So in the last section, we looked at how we can find the area of a region on a graph, which really was not a new idea for us. But now we're going to extend into three-dimensional solids. This has a lot of applications in manufacturing, especially where you're trying to determine the cost of producing certain items depending on the size and casting, making molds of things. So there's a lot of different uses where this would become important. So what we're going to be doing is looking at a method that we're going to call like slicing. Okay, so if you think of, for example, a loaf of bread. When you buy a loaf of bread at the store, it's been sliced into all of these individual slices of bread. But when you stack all of those slices together, you get the full loaf of bread. So you could find the volume of the loaf of bread, or you should be able to theoretically find the volume of one bread slice and use that to multiply across the length of the loaf of bread and come up with the volume that way as well. That idea of slices of bread, essentially, is how we're going to find volumes of solids with known cross-sections, meaning their cross-sections are going to be something that we can determine the area of, okay? So some common cross-sections, this is where your area formulas are going to come back into play, would be things like squares, rectangles, semicircles, trapezoids, triangles. Obviously, all of these shapes are going to be things that you'll need to be able to find the area of. Now, to help you visualize this before we really start talking about the calculus, here's an example. We'll come back to the definition and stuff here in a second. But here's an example of we have the curve x equals y squared, which is this horizontal parabola, and the equation x equals 9, which would be this vertical line. So it creates this sort of like capped off parabola boundary on the bottom, okay? We want to find the volume of the solid that would be created that has that region as its base, and then every cross section, as you were to move horizontally along the x-axis, every cross-section would be the shape of, in this case, a square that is perpendicular to the x-axis. Now, the hardest part about this is trying to visualize what that would actually look like. So I have a couple of different visuals here that I want to show you. So this example is slightly different than the one that we just looked at because ours is actually oriented along the y-axis, you can see here. But the solid is going to be a very similar shape. We have this almost parabola type shape, kind of looking right here. It's not quite a parabola because it's pointy at the bottom, but we have, well, actually the base of it is down here. We have this parabola shape. And then we're cutting it off with a horizontal line. So we have the region there. If we rotate this, we can see what the bottom region is shaped like. That is the very bottom of it. So that's what that region is at the bottom. And then when we are cutting, in this case, we're cutting these slices perpendicular to the x-axis, you can see that when we cut it this way, we're getting this sort of almost like a trapezoid, but it has a rounded top. Here's another way that we could slice that one. Nope, not that one. This is more like what the example we were just talking about was, except the axes are backwards, okay? For this one, we are slicing, it's that same shaped base, okay? But you can see the cross sections here when we take just one little slice, almost like that loaf of bread, the cross section there is a square. This one might be more of a rectangle because it's not exactly the same. We can look at it straight down and we see there that it is a rectangle. But so just like how when we use a Riemann sum to add up little slivers of rectangles to find area. To find volume, we're going to add up thinner and thinner and thinner slices. And so basically we want to add together infinitely many slices of bread, slices of volume, to figure out what that is. So in order to add up all of these rectangular slices all the way up and down this value, if we think of those each as a very, very skinny rectangular prism, what we want is we want this width to approach 0. So if the width of your prism was essentially 0, that means this volume would just be equal to the area of that cross section. And we're going to add up that volume with 0 width infinitely many times over our integral, and that's how we're going to come up with the volume. Here is another example. This is a totally different shape, but this is one where the base of our figure is a triangle, okay? Where we would want to integrate would be this triangle base, so we would want to add up the slices this direction, but you can see that the cross sections every time are these little triangles. Appears to be equilateral in this example. And so what we're going to do is take all of these slices and add up all of those little slices all along our interval here, which appears to go from 0 to 2. That's how we're going to determine the volume of this shape. So everything we're doing is looking at infinite slices. So here is how the volume works. If you have cross sections that have an area of A of X, now that formula is always going to change depending on the shape. If it's a rectangle, your A of X is going to be like length times width in terms of X of some sort. So if your cross sections are perpendicular to the x-axis, then you're going to integrate with respect to x. So your limits of integration are going to go along the x-axis. So in this case, our limits of integration would be like from A to B like this. And our cross sections are going to be perpendicular to the x-axis. If your cross sections are perpendicular to the y-axis, then we're going to integrate with respect to y. And so C and D, your limits of integration, are going to come off of the y-axis, and then your slices are going to be perpendicular to the y-axis in that regard. So to get us started, let's just work through one example. Let's go back to number 1 here. So we want to let R be the region bounded by the graphs of x equals y squared and x equals 9. So if we're just thinking about that in 2 dimensions, looking at our x and y axis, that graph looks like this: a sideways parabola, and then this vertical line here that is at 9. So this region is the base of our solid. So every single one of those squares that's drawn over here is going to be sticking straight out from the screen. It's like it's coming right towards your face. But what we do know is that the base, the width of each one of those squares, is going to span this distance. Okay? So that is going to be the side of our square. So I always like to look at the shape kind of off on its own. So in order to find the area of a square, I need to know this length right here, which is exactly what we have on the graph. Now, how would we find the distance between those 2 curves? It's exactly the same way that we found the representative rectangles when we were finding the area between 2 curves. it's going to be the top curve minus the bottom curve. Since these rectangles are perpendicular to the x-axis, we will need to integrate with respect to x. So that means I need to rearrange my equations. So I know that horizontally this is x equals y squared. But if I solve that for y, I get y equals the positive square root of x for the top. And I get y equals the negative square root of x for the bottom, because we get plus or minus when we square root on both sides. So to figure out the length of that square, the length of one side, it's going to be top minus bottom, which is going to be the square root of x minus negative, square root of x, which is going to be 2 root x. And so that is how we determine the side of our rectangle. Once we know what the side of that rectangle is, we can set up the area formula for this square. Now, the area of a square is going to be side squared, or base times height, but base and height are exactly the same. So this is going to be 2 times the square root of x squared, which means square the 2 and square the square root, so we get 4x. So that is the a of x formula that we want to integrate. So now to find our volume, which again is what we're trying to do, we're going to take all of these squares all the way along here to create this solid piece. And we're going to sum all of those up from, this is starting at 0, and we know that this right here is 9. So we're basically integrating from here all the way over to here, if you look at the blue graph. And we're going to add up the area of all those rectangles along that way. So the volume is going to be equal to the integral from 0 to 9 of our area formula, which is 4x dx. And so that's a pretty easy one to integrate. We get 2x squared from 0 to 9. So this comes out to 162 minus 0. So the volume of this figure with all of these square cross sections is 162. Now, they didn't give us any units or anything like that, so we don't need to put that. But if this was centimeters or whatever, it would be cubic centimeters or cubic meters or whatever it might be, because we just found volume. And so that's just one example to help you kind of get thinking about what this is going to be doing. Let's look at using the same base figure. So we'll keep that blue graph and we'll use a rectangle instead this time. And it's kind of small, so it's kind of hard to tell, but this rectangle is labeled that its height is going to be 2. So no matter where I draw these this time, the height of the rectangle is always going to stay the same. But you can see that where I draw the base here is what's going to change. This is going to stay 2, but the width of our rectangle is going to change. Now, again, looking at the graph, this is the same as what we just drew last time. Okay, that's that red segment that's on our blue graph in the corner. So we know that the width of that rectangle is 2 square root of x. So here's the figure that we're finding the area of this time. Okay, it is always going to have a height of 2, but the width is going to be 2 times the square root of x. And again, that's based on the work that we did over here. So the area of this rectangle is always going to be 2 times 2 root x, which is 4 times the square root of x, which I'm going to write as 1/2 to make it a little easier to integrate. And so now all we have left to do is to integrate and sum up all of those rectangles over the interval, which is going to be, again, from 0 to 9, of 4x to the 1/2 power dx. So let's go ahead and figure out what this is going to look like. I'm going to go ahead and pull out the constant multiple here. Save that for the end. So when I add 1 to the 1/2 power, I get x to the 3/2 power. And when I divide by 3/2, that makes it 2/3 from 0 to 9. So our volume is going to be 4 times 9 to the 3/2 is 27. 2 times 27 is 54. So we have 54 over 3 and then minus 0 again, which is nice. And I'm pretty sure 15 divided by 4 or 54 divided by 3 is 18. So that's going to be 4 times 18, which is 72, I believe. So 72 would be the volume of that figure. And again, that figure is a little bit different. It's not going to be rounded like the other one because no matter where we are, the height is always going to stay 2. So this one is actually kind of flat like that versus the top one, which since the heights were also changing, we're getting kind of this rounded figure like this. The hardest part about this is kind of visualizing what is happening, but think of it as one single slice. That's really going to help. We'll do some more examples in the next video.